Figure 1 shows a quadratic and a straight line, and we're asked to find the inequalities that define the region in between them. Let's first of all look at the straight line. So I've actually got 2 points. I've got 0, 25 and minus 2, 13. I can use that to find the gradient. It's going to be the change in y over the change in x. y2 minus y1 over x2. Make sure you use a 0 to be consistent, minus minus 2. You could draw a triangle and add the dimensions on if you want as well. So 12 over 2, which is 6. We don't even need to use y minus y1 is m, x minus x1 here, because we have the intercept. We can straight away write down that y is equal to 6x plus 25. That bit is sorted. Now for the quadratic. So we have the minimum point and another point on there, which happens to be the intercept. That is enough to get the quadratic. Just going to backtrack a little bit. If we had a quadratic in completed square form, something like this, then we could actually write down the turning point. It would be 4, 9, because this term here is always greater or equal to 0. It can't be negative. So the smallest it could be would be 0, and the smallest the function could be would be 9. And then it would be equal to 9 when the bracket becomes 0, which is when x is 4. So that's where the 4, 9 comes from. If I was to put, say, a 5 in there, then my function would sort of be steeper, so it would end up being a bit like this, for example, but it would still have the same turning point because this would still be 0 when x is 4. We're going to be applying that idea now, but in reverse, because I know how to get the turning point from completing the square. I can actually get the completed square form from the turning point. So I've got x plus 2 squared plus 13, which gets me the minus 2, 13. However, like I said, there's lots of functions that have that turning point, so I just need to put an a in front. Loads, see, it's like that would have that turning point, that one, but there's just this one function that's going to go through 0, 25. So to find a, I'm going to substitute in x equals 0 and y equals 25. 25 is going to equal 4a, because I'm going to do 0 plus 2, which is 2, square it to give 4. 4a plus 13. That means 4a is 12, a is equal to 3. And I've got it. My quadratic is y equals 3, x plus 2 squared plus 13. Just for the inequality bit now. So the region is going to be below the line, and therefore I actually need that y is going to be less than or equal to. I mean, it can be on the line because it's a solid line. Y is less than or equal to 6x plus 25. And we also need that it's above the quadratic. So y is greater or equal to 3x plus 2 squared plus 13. Now, I think that answer is absolutely fine. Sometimes you get more than 2 inequalities and you can't possibly combine them together. And the answers, they do combine them together, and it is quite nice. So they actually write the final thing as 3x plus 2 squared plus 13 is less than or equal to y, which is then less than or equal to 6x plus 25. So you might prefer to write like that. If you had another inequality with a line like that, then you couldn't do that. So I'm pretty happy with mine, and I've just sort of got used to writing them like that. But the mark scheme does get that bottom one, and you might prefer that. Anyway, well done. One final comment, I just looked at the mark scheme and they actually use a less than. They don't actually allow it to equal, which I'm not really happy with, because when I always learned that when you have a solid line, it means you're including that in your region. If you want to use a dotted line, then you're not. I can see where they're coming from. They're saying that it's the boundary, but it's whether we should include the boundary or not. So anyway, both are accepted. I still like my answer. I'm just telling you that if you look at the mark scheme, you'll see it's slightly different.